Hey everybody, Dr. A here, and in this video we're going to be exploring an example of internal torque moments. So let's go ahead and get started. In the given information, we're being asked to use the method of sections to determine the internal torque moment in each segment of the shaft, which has a circular cross section. So in the figure that we're given, we have a fixed connection at the left end, and then we have this 3D view of a shaft coming out of that fixed connection that has two different torque moments being applied to it. Near the middle, we have a 3 kilonewton meter torque moment, and then at the end of the shaft, we have a 2 kilonewton meter torque moment going in the opposite direction as the 3 kilonewton meter torque moment that's near the middle. Now notice we don't have dimension lines here, so we don't know exactly how long the shaft is or where these torque moments are being applied, but we can still answer the question, all right? So let's go ahead and get started. We're going to write solution here, and we're going to use method of sections. Now, what we do is we cut a section through each segment after every time something changes along the member. So this method of sections, it's the same method of sections, same process that we've seen before in statics or in other aspects of mechanics of materials, okay? So here's what I'm going to do. I'm going to start at one end of the shaft, and I'm going to cut a section through the middle of a segment, and then I'm going to cut another section through the other segment after something abrupt happens. We have this 3 kilonewton meter that torque moment that represents an abrupt change somewhere along the length of the shaft. Now, if you remember from method of sections, there are two ways of handling a method of sections process, right? You start at one end of the system and you successively move towards the other end. So could we start at the left end of the shaft, and could we, make a cut section through this segment and look at a left free body diagram? The answer is yes. But in order to do that, we would first need this torque reaction, right? There's a torque reaction at the fixed end, which we can calculate. That's fine. So let's go ahead and get that torque reaction. Although remember, we don't really need it because we could look at a right free body diagram which bypasses that torque reaction. So I'm going to make a note here. I'm going to say, let's compute the torque reaction, okay, at the fixed end, although we don't need it, okay? And let me spell torque a little bit better. Got excited with my pencil here. So if we compute the torque reaction, what we're going to do, just to be proper, we're going to draw a free body diagram of the entire system, all right? And we're going to say that we have this torque reaction right here. So I'm going to say TR for torque reaction. And then we draw on here our applied torque moments. That's 3 kilonewton meters. And then we've got 2 kilonewton meters here. Okay. Now remember, this torque reaction, it's unknown right now. So I'm assuming that it is oriented in this particular direction. All right. And so how do we calculate this? Well, the best way to do this systematically is to draw a viewpoint here. I'm going to draw this as a little eyeball, and I'm going to say, hey, right now I'm looking at the end of that shaft. Okay, so this is a little eyeball looking towards the shaft. So when we do that, what do we see? Well, we see a circular cross section. That's the shaft. And then we see that 2 kilonewton meters first. Now, from this viewpoint, the 2 kilonewton meters is going to be going clockwise. Now, behind that, we see the 3 kilonewton meters, okay? And that 3 kilonewton meters is going to be going counterclockwise based on what we see here, okay? So this 3 kilonewton meters is going counterclockwise. And I'm drawing this dashed to represent like a hidden figure, right? In graphics, we know dashed figures are hidden. They are behind or underneath something, okay? Behind that 3 kilonewton meters, we have the torque reaction T sub r that is going, looks like it's going counterclockwise based on this viewpoint. So then what I can do is I can say sum of the torques equals 0, and I can say counterclockwise is positive. And I'm going to put a little symbol here. I'm going to say based on that viewpoint. So I'm going to redraw this little eyeball here, okay? And so that means that I'm looking at this figure for my directions of these torques. And so I'm going to be able to write T sub r plus 3 kilonewton meters minus 2 kilonewton meters equals 0. And then what do I get for T sub r? Well, I get -1. Let's see if I can draw a negative sign that looks like it makes sense. -1 kilonewton meters. But what does that negative sign mean? That means that you've got a reaction of 1 kilonewton meter going the opposite direction of what we assumed in this free body diagram, which based on this viewpoint, we assumed T sub r was going counterclockwise. So that means it's really reacting as 1 kilonewton meter going clockwise, okay? Now, that's the torque reaction. Do we really need it to solve the problem that was asked of us? And the answer is really no, right? With method of sections, you make a cut section through a segment and you look at one side of that cut section or the other, all right? So we can make a cut through this segment that's in between the reaction and the 3 kilonewton meters. We make a cut right here, and we could look at a left free body diagram, in which case the TR reaction is there and we need to use it, or we can make this cut and we can look at a right free body diagram, which will include the 3 kilonewton meters and the 2 kilonewton meters, and we need to use both of those. We could use either free body, it doesn't matter, okay? Since I went through the trouble of getting TR, how about we look at a left free body diagram for illustrative purposes of this example? So I'm going to say, let's make a cut 1, and I'm going to say look at left free body diagram, okay? So when we do that, what do we see? Well, we have the shaft here, and we have a cut somewhere in between TR and the 3 kilonewton meters, but it's not going to include that. It could be a cut anywhere up to the 3 kilonewton meters, all right? And then we calculated TR is going in the clockwise direction based on that initial viewpoint, right? So that TR is 1 kilonewton meter. And then when we make this cut, what becomes visible here? Well, an internal torque. I'm going to call that T1, okay? And so what I'm going to do is I'm going to create another viewpoint, and I'm going to look into the cut, all right? And so what do I see here? Well, I see a circular shaft. I see that assumed T1 that I'm trying to find, and I see that torque reaction of 1 kilonewton meter that's behind it as a hidden line. And so I can say sum of the torques equals 0, counterclockwise positive, using this new little eyeball. And I'm going to have, T1 minus 1 kilonewton meter equals 0, T1 equals 1 kilonewton meter, and that is going in the direction that was assumed in this green viewpoint. Okay, am I done? No, but that's one of my answers, right? What's my next process? What am I going to get to next? Well, I need to make a cut in between the 3 kilonewton meters and the 2 kilonewton meters. And when I make this second cut, what do I look at? Well, I can look again at a left free body diagram, which now will include TR and the 3 kilonewton meters, or I make this cut and I look at a right free body diagram, which is much more simple, which only includes the 2 kilonewton meters. Let's look at this right free body diagram. It's a bit simpler, okay? So I'm going to say cut 2. I'm going to say look at right free body diagram in this case. All right, so there's that end of the shaft. There's the cut. And then what's showing up at the end of the shaft? Well, there's that applied 2 kilonewton meters, okay? And what's going to be internal here? Well, I've got T2 that I'm looking for here. Now, here again, you can put your viewpoint really anywhere, okay? You could put the viewpoint out here, and you can look into the cut, or, let's erase that, or you could put the viewpoint out in front and look at the end of the shaft. So guess what? Does it matter where we put our viewpoint? No, it doesn't. It does not matter where we put our viewpoint. But you just want to be consistent on a particular step and know what you're doing. So how about this? How about I just put my viewpoint here and I look into the cut, okay? So what do I see? I see a circular cross section, and then I see T2 going clockwise, and I see the 2 kilonewton meters going counterclockwise. Now again, think about what the eyeball sees. When the eyeball is here looking into the cut, it first sees that T2, but it's going clockwise, okay? Look at it here, all right, from this perspective. And then behind it, you see the 2 kilonewton meters going counterclockwise. And so I'm gonna say sum of the torques with my eyeball equals 0, counterclockwise positive. And so here I'm gonna have 2 kilonewton meters minus T2 equals 0. So from this perspective, T2 is 2 kilonewton meters, and this is going clockwise from this viewpoint's perspective. Okay, now you might be wondering, how come I was able to do this and it seems like I just ignored this 3 kilonewton meters? Well, I didn't really ignore it, right? I mean, the 3 kilonewton meters is built into the reaction, right? The 3 kilonewton meters was incorporated into the reaction that we calculated earlier, which is built into this 1 kilonewton meter, which was again built in to cut 1. So the essence of this 3 kilonewton meters is there. It's in the process. Even though when we did method of sections, we kind of bypassed it, right? We made a cut here and looked at a left free body, and then we made a cut in between the 3 and the 2 kilonewton meters, and we looked at a right free body, okay? So again, method of sections, it works the same way with torque-loaded shafts as it does with axially loaded members and beams that we've studied before, okay? And so what's our answers finally? Well, our answers are T1, 1 kilonewton meter, and T2, 2 kilonewton meters. And again, be very mindful of where your viewpoints are, okay? If you found this video helpful, please hit like and subscribe, and please be on the lookout for other content like this. Thanks for watching.